Okay, so lecture 14. So let's recap what we did before. Let's recap. So what we've gone through is about connectedness, right? So what is the connectedness? A set is connected if there's no separation. So what's the separation? A separation is what? Is a pair of disjoint, open, and non-empty. Okay, non-empty is a separation of A in so the separation of let's say a topological space is a pair of, so because we need to talk about open, right? So I need to tell you what set are open. So that's why I need to put a topology here. Okay. So a separation of a topological space is a pair of UV, okay, such that they are disjoint, open, and non-empty. Is set such that what? What does this two set do? S equals to U union V. Okay, so this is a separation. So then we define that a topological space is connected if there is no uh, there's no separation. Okay, so in this case, right, to prove something is not connected is easy because you just need to find two open sets to separate your topological space. Okay, that satisfies the three properties here. Okay, if you want to show something is connected, then you need to show by showing there's no such kind of separation exists. And if it is a subspace, you want to prove subspace connected, we manage to deduce that as long as none of the set contain limit points of each other, then they will form a separation, okay, because the openness will be implied. And the last few property we've gone through is if you have two sets which are connected separately, but they have a point in common, what happened? Once I take the union, they are all separated. Okay, does it make sense? Remember the proof? Okay, so if you have two connected subspace, okay, with a point in common, then the union of space is connected. Okay. And then from here, we will define something called the connected component. Okay, what is the connected component? Which is the largest connected set containing A. What does it mean by largest here? So it is defined to be the union of all connected sets in X that containing A. So this construction is a bit similar to how you prove the assignment question, right? A lot of you write the solution to me that an opens for the question of open set can be written as a countable family of interval, and you say, for every x, find the maximal one. So this is what the maximal, the largest connected set doing. Okay, how do you construct this largest one? You need to union all the connected set that contains A. Okay, take the union of all. And then we say that this connected component form partition of X. Okay, so in this case here, it will give the equivalence relation on X. And this one remark that we didn't make last time is, you can see that the number of connected components, right, of a topological space is actually a invariant, topological invariant. So if you have a topological space, okay, you know what set are open, then you can try and go and look for these connected component. And then this connected component won't change. The number of connected component won't change. Okay, given a topological space. Okay. So this topological space, of course, are not just space itself, it's not just set itself. This set have to come with topology. So maybe you have a same set, but a different topology, maybe the number of connected component will change. Okay, so it really depends on what things are open inside your topological space. Does it make sense? Okay, if you have a set, you have a topology, then the number of connected component is fixed already. Okay, so this is what we call a topological invariant. Does it make sense? Because this invariant depends on the topology. Okay. So in mathematics, we typically want to look for these invariants because we want to see whether these invariants will classify our topological space or not. Okay. Based on this number of connected components, can we understand the property of this kind of topology, topological space? For example, topological space with only two connected components, and topological space with three connected components. Are they the same or not? Okay, do they have similar property or different property? Okay, so we're trying to use these invariant, to classify topological space. And I think this thing we can skip. And maybe this one I didn't make much comment about this last time. So this theorem says that if A is connected, and if you consider B as a superset of A and a subset of A closure, then B is connected. So what does this mean? This means that you might have more things, you potentially have more things than A, but the things that you add in is what? Is either, it's actually the limit points, right? Because everything in A already in B. So if you want to stay inside A bar, what's the difference? A bar is what? A plus limit point of A. So here B is like, you can imagine this B is like adding some of the limit points. Okay, limit some or all of them also can, because B could be equal to A bar. Okay, so it says that even if you add some limit point back to A, then that space is still connected. It doesn't affect the connectedness. Does it make sense or not? Okay, let me give you an example here. Let's say, so there's a non-example here. Let's say your A is this open ball. Okay, so A bar is the closed ball. Okay, but let's say you add B such that B is greater, B contain A bar. And this part is also B. I also add this part in. So somehow there are two connected components here. Okay. Of course, I was considering the R2 standard topology here. Okay. But what's the situation described in the theorem? So let's say I have an open ball here. Okay. And then I fill it in. So I take the open ball. It is connected, right? Open ball is connected. And what do? What's the closure of this open ball? It's the closed ball. Okay, it's a closed ball. So meaning I take the boundary as well. Okay, but what kind of B I can do here? I can potentially just take, you see, maybe I just take here up to maybe somewhere around here. But here I still doesn't include the boundary. Then this B is still connected. Does that make sense? Are you seeing what am I trying to do? Okay, you start with an open ball. So open ball here is the blue one. Okay, dotted on the boundary and then include the interior. And then C is what? C is interior plus the boundary, which is the red one. Okay, and then the yellow one is some set that are adjoint limit point to the open ball. So how do I adjoin? Maybe I add in half of the limit point in. Okay, and then leave the rest the same. So it's like still, how to say? It's still kind of, it's still, how to say? There's a Malay word, it's like bocor. Bocor. You guys know bocor? What is bocor? Don't know. You don't know bocor? Huh? 漏洞, 破洞. Okay. So maybe I just fill it fill in half the boundary points. Okay. But the result is this B is still connected. Okay, it's still connected. Okay. So this is the result that we had last time. Okay, so far so good about connectedness. Okay, maybe you realize my notes get a bit longer than the usual one. Because our speed getting faster, and I left a lot of detail, ask you to work it out, right? So those details, some of them I'll put inside lecture notes. So make sure you really read the lecture notes, okay? Otherwise, you won't know what I want you to know. And I will particularly test on those things. Be careful. Okay, I don't want you to just look for reference yourself. This is the same as when you do assignment question, you know. Some of you tend to write too much. You know why this situation will occur? This proves that you didn't listen to the lecture. You don't know what has been done in the lecture. So you don't know whether this result is already proven or not. So you tend to prove everything inside your assignment. Okay. I'm not trying to condemn you, but please take note of this. So you need to understand what result is already proven in lecture, and then what result you can straight away use, quote it. Okay. So tutorial is another way to prove new result. Okay, so why I ask you to do tutorial? It's not just for fun. It's not also just for your understanding. Because tutorial result you can also use in your assignment. Okay, does it make sense? So everything, how to say, come up from me, you can use it. Okay. Yeah. Typical assignment question won't be too long, the solution. I already released the solution, right? You can compare the length of my solution and the length of your solution. Okay. It shouldn't be too long. Maybe sometimes I'll put long question, but there's just a very few, not every question like that. And also I posted out the sample solution by Wen Chuan and who? Jian Xiang. Yeah, their solution, I didn't say they are perfect, but you will find that their solution is very easy to read, very clear, step by step. Okay, you can know whether this is correct or wrong easily. Okay, so this is the quality I want you to have in your proof writing. Okay, you need to prove every sentence that you write. Okay, does it make sense? Okay or not? Okay, we will talk more about that later. Okay, so let's continue. So today we will go to a more specific topic, which is called path connected. Okay, so what is path connectedness here? So just previously we talked about connected is using open set. Okay, now here path connected, meaning we need to introduce path. Okay, so what is path? So we need to define path first. So suppose we have a topological space, okay, and a 0 to 1 interval with Euclidean topology. So meaning the normal topology on R. So for any 2 points, A, B in X, a path from A to B in X is a continuous function. Okay. So continuous function from where to where? From the interval 0, 1 to x. First of all, do you think this definition makes sense or not? Does it make sense? Does it make sense to talk about continuous function from this interval to x? Make sense or not? Why does it make sense? Huh? What is the definition of continuous function? Yes, pre-mesh or open set is open. So can you talk about open set in X or not? Cannot. Yes, right, because I know the topology on X. Can I talk about open set in 0, 1 or not? Yes, I know the topology on 0, 1, which is the usual Euclidean topology. Okay, so we can check whether the inverse image of an open set in X under this F is open. Okay, so we can look at this kind of continuous function. So path here, be careful. Path here, maybe you can imagine like this, but really it is defined by a function. Okay, function from where to where? From the interval 0 to 1. Okay. So although in your mind maybe path is just some walkway like that, but the definition here is this function f. F from this interval to this. So you might imagine, this line is straight. This line is a bit bending. How to map? How to map? So you need to tell me which point goes to which point, and then you need to do it continuously. Sense? Okay. There's a different way to map, right? I can send maybe 0 to here, maybe 1 to here, and then middle point to there. But is that map continuous or not? So you need to make sure your map is continuous. Okay. So I mean, one example will be something like this one. So you send nearby points to nearby points. One example. Okay, so you cannot randomly send. Although maybe there's a bijection there, but we need continuous, right? Continuous function. All right, so a path is a continuous function. So next, when do we say a topological space is connected? So a topological space is path connected if, you want to guess? Want to guess? So you got, yeah? Yes, that's right. So if a topological space is path connected if for every 2 points in X, there is a path in X. So every point have to stay in X for this path from A to B. Can A equals to B or not? Can A equals to B? Can. If A equals to B, what kind of path you can take? Yes, constant path. Okay, just take constant path. So meaning you send the interval 0 to 1 to just 1 point. Okay, starting F, so F0 is X, F1 is also X, and then for all the T in between 0 and 1 is also X. Okay. Example, if A equals to B, then you can define F from 0, 1 to X to be T sending to the point A. Is constant function continuous or not? Continuous, right? Last time we proved already. Okay, if not, go and recall how we build continuous function. All right. Let me see. Let me see. So we can also talk about a subset of a topological space to be path connected. Okay. So a subset A in a topological space is path connected if it is a path connected topological space. Okay, so when is it a topological space? When you consider it as a subspace topology. Okay, when you consider it as a subspace. So this is similar to how we define connected subspace, subset. Okay, connected subspace. Okay, should we do some algebra on a path? Are you guys interested or not? Algebra on path. You guys interested to do algebra on path? Okay, so maybe we can do some. Actually, it's not quite, at least not quite important for our context. But maybe we can do some detour on algebra on path. So I think this will be useful if you're gonna take algebraic topology later. As for our course, I think not too important. For our course, you just need to find a path that do the path connectedness. Okay, so right. So let's say if I have a path 0, 1, x, a path, okay, from A to B. Okay. Can you define a backward path or not? Can you define a backward path? Can you define a backward path or not? So let's say you got a point A here, B here, and then you got a F going forward. Can you define a backward path? How? Sorry? How to change? Yeah, so you can take backward path to be GT, where GT equals to F on 1 minus T. Does it work? Does it work or not? When T equal to 0, what happened? It is F1. So F1 is the endpoint. When T equals to 1, okay, when you finish the path, you are actually just starting it. Okay, so you are going backward. Okay, no? So the middle T also work the same. The T in between 0 and 1. Does this remind Leong Yuan or Gary or not? Huh? Yeah, we did the fundamental group, right? Yeah. Okay. So this is a backward path. What else we can do? We can also compose path, Okay, we can compose path. So for example, what? So for example, let's say if F again is a path A to B, and G is a path from B to C. Can you compose them? Can you compose? Compose. Shouldn't use compose, or later you confuse with the compose function. So maybe combine also can. Can you combine the two paths F and G so that you get a path from A to C? Can or not? If you have a path from A to B, again you have a path from B to C. Can you compose them? How do you compose them? Let's say we call this a HT. How you compose them? Do maybe FT first and then do GT. Is it? But how you do it? Sorry? Sorry? 0 to 1, 1 to 2. But remember, what's the definition of path? Only can start from 0 to 1, right? So how? Make it shorter. I cannot say make it shorter lah. Should be say make it faster. We need to reparameterize our curve. Okay, let it run faster. Okay, so how to let it run faster? So for FT, I make it run double speed. Okay, so that I just need to take time from 0 to half. Okay, and then how about GT? GT is going from T from half to 1. So what should I do? How should I parameterize? How should I parameterize it? Sorry? 2T. 2T enough or not? 2T minus 1. Okay, so you can use G of 2T minus 1. Yeah, so this is the first exercise you will see in algebraic topology class if you're going to take it. Okay. Yeah, how to compose path, how to take inverse. Okay. But I think not quite useful in this course because we just want to check whether one topological space is connected. Okay, let's continue. So how does it relate path connectedness and connected? So if a topological space is path connected, then it is connected. Okay, but not the other way around. Okay, later we'll see an example that something is connected but not path connected. Okay, you cannot separate by open set. Okay, what did I say? It could be connected but not path connected. Okay, you cannot be separated by open set, but you also cannot join using a path. Okay, I think this is correct. Fair enough. Okay, you cannot join any 2 points using path. Okay, the other direction is wrong. Okay, only one direction works. So if it is path connected, then it have to be connected. So how to prove this? Contradiction or contrapositive. Okay, so suppose it is not connected, then there's a separation. Okay, if it is a separation, what do you do? Okay, you say first. You say first. He say one, you say one. Okay, take turn. Okay. No, not really. You want to say something? Similar argument. No, I mean how you argue. There's no path. I just separate them using open set, right? Why you deter me from building a path? Correct or not? Okay, let me write down the assumption first, and then you guys try and think about it again. So suppose, yeah, any idea? Why not? Why not? Why not? It's disjoint. You cannot. I think I get what you say. Yeah. So you mean, let's say our open set. Wait, let me draw it. Sorry. Later we'll use that argument. Let me think what he's trying to do. So you mean, let's say we have a separation like this, right? So I mean, within this open set, maybe they're connected, maybe they are not. Depends. But you can always take 2 points with this 2 set, right? 1 point from one empty, not empty, disjoint open set. Okay. And then if you're gonna try and build what path, so you're gonna build interval map from the interval 0, 1 to this space continuously. What you need to do is, okay, somehow you need to pass by this disjoint thing here. Okay, so this is somewhat your argument there. Okay, I think it's not too far. I think it's not too far. But you need to argue why this disjointing cannot deter you from building this map. What's the lemma? Oh, nice. Yes, we have one lemma like that. So if you are a connected subspace and then your space is not connected, then that connected subspace must lie in one of the connected subspace. Yes, correct. You can use that argument. Good, very good. Yes. So this is a different proof to that because I'm not going to say that proof now. So what's the proof here? So here we will use a continuous image of a connected space is connected. Okay. So let's see how we use this. So suppose there's a suppose this space is not connected, and and what? And so similarly, we do similar things. So let UV be a separation of X. Okay. Since U and V, what is this? Since U and V are non-empty, non-empty. Okay, not this one. Non-empty. So there exists U in U and V in V. Okay. And let's say we have a path. Okay, let's say we have a path in X connecting U and V because XT is path connected. But what? But F of this interval here intersect U union, sorry, maybe just put comma, and F of intersection image intersect with V is a separation of the image of 0, okay, which is a contradiction because a continuous image of a connectedness should be connected. Okay, but also you can use a Brand's argument. Okay, if you have a connected subspace, they have to lie inside one of them. Then you cannot connect the others, point the other in the other set. Okay. No. That one is the proof for that statement. But the proof you want to use that result, right? So the result here is, at first you say that there's a path that connect these 2 points, but since we already separated, then this path should either lie here or lie here. If fully lying in one of them, then it cannot connect the other point. So it contradicts it as a path. Yeah. That one is contradicting the F2B as a path that connects U and V. But here the contradiction is the connectedness of the image. Yeah. Okay, so there are different ways you can solve it. Okay, I think the most important thing is this one, and then we will look at few examples. Let's look at some examples. Okay, let's look at some examples. Some examples here. So let's look at the unit ball Vn. Is all the point in Rn such that the length is less than or equal to 1. So is this space path connected or not? Yes. Okay, so if you say it is path connected, meaning for any 2 points, you need to generate a path for me. Okay, so what kind of path you can take here? Straight line path. So what is the straight line path? So for any x, y in Bn, how do you form this path here? Y minus t times x plus ty. So what do you need to do? You need to check that for every t, this is a point in Bn. Okay, so for every t, this is a point in Bn. Is it true or not? True. Can prove it or not? Use? Yes. So you need to check that ft is in Bn for all t. Okay, you need to check because you need a path in the topological space itself. Okay, so we need to check that this is true. So how to check this? So let's see. So what is the modulus of this whole thing here? Okay, so modulus of this two, you can use triangle inequality to split it. So once you're using triangle inequality, what do you get? So you get this. We use double bar, single bar or double bar. Let's use double bar then. I want to confuse with the usual one. Okay, and then we can further bring our inequality into it. This is the scalar property, right, of norm. Okay, but S and T are the points in the unit ball. So in particular, their length is less than or equal to 1. So this is really just the value of 1 minus t plus the value of t. But t is what? 0 to 1, always positive. Okay, so this is really just 1 minus t plus t. So this is equal to 1. Okay, so every point is in our topological space. But why we call this a straight line path? Why Ziqian said this is a straight line path? Sorry? Linear combination of linear transformation? Yeah, something, yeah, convex is defined using this kind of thing. But how to straight away see this is a straight line? That's right. But you need to argue why is it linear, right? Where's the linear? Normally linearity see from the gradient, right? So you need to somehow make it into you get what I mean? What should I say here? What should I say here? I think I can read. I think we can rewrite this. We can rewrite this formula. So this is y minus x times t plus 1. Plus x, yes. Yes. Okay. Yeah. So y minus x become a direction vector. Okay. Scale with this. Wait. Scale with mx plus c. That one shouldn't say it's a scale, right? It's like y equal to mx plus c. M is this thing, x is this thing, plus c is this thing. This. Oh, okay. You can imagine it that way. Yeah, you can imagine it that way. Yeah, you can imagine that way. Yeah. Because I'm treating this t as a single point. So we have 1 point and then you got 1 point. So this is like, this is your starting point, and then this is your direction vector. Okay, good. So these are just calculus thing. We just make it look fun. Okay. Yeah, we make it look more fun. Okay. So what else? Let me quickly finish up the examples, and then we can. Okay. Let me see. How about this one? I think this one also quite interesting. How about a punctured Euclidean space? So what does a punctured Euclidean space mean? You just take Rn and then you puncture it. Where do we want to puncture it? Any point also okay, but just repeat the origin. Okay. So is this space path connected or not? Huh? Yes, how? Let's say we just imagine in R2 first. Let's say we punctured it in the middle. Okay, there's a hole here. So what can you do if I given you 2 points? Yeah, simple. This is not a trick question. This is not a trick question. This is so I don't want to see obvious, but quite obvious. I mean, give me a path. Correct or not? Give a straight line, no? Yeah. So why take so long? Scare me, scold you. Yeah. So if let's say these 2 points say, oh, you want to take straight line also, then you need to make some detour. Okay, you don't take only the straight line. Okay, you take a detour around this function. This is complex analysis, right? Have you guys did the contour thingy? Oh, not yet. Contour integral. Okay. So you make a detour around this puncture. Puncture space is quite, how to say, quite, how to say, the frontier use it, the research frontier use it quite often because they treat this puncture as a singularity. Okay, we want to study some singularity space. Okay. Yeah, in particular for physics, this is very important when they study the black hole. What happens around black hole? Yeah, so I think we should get rid of this so that don't confuse people. And to take this detour here. Okay, let's finish out one example and then we will take a break. And then we will discuss assignment. So the last example I'll talk about is called the topologies sine curve. I don't know whether the name is topologies sine curve or topology sin curve. You sure it's sine? It made me feel like they want to put it as a sin because when you put sine short form, you also sin only, right? This one is also fine, but I think sin is more contextual. You know why? This space is notorious. So this is connected, but not half connected. This space is connected, but not half connected. Okay, I haven't tell you how to define this curve, right? So how to define this curve? So this curve, I call it x. Okay, so what is x here? Is equal to the point in R2 such that y equals to sine 1 over x. And x is going from 0 to 1, including 1, but not including 0, because it's undefined at 0, 1 over x. Okay. What is this curve? Have you come across this curve? Sine 1 over x. What's this curve looks like? Sorry? Vibrating, right? Vibrating. Oscillating, we will say. Not vibrating, oscillating. Okay, so oscillating, how does it oscillate? How does it oscillate? Yes, so you oscillate around -1 and 1. And then when you get into 0, it get very frequent. So Can I draw it? Good. Let me try. Okay, let me draw it slowly. So something like that. When it is close to 1, it oscillates very frequent. Have you guys seen this in the MA example? Huh? So in what occasion you will introduce this example? For example, to what? Oh, I don't mean MA2, I mean MA1. Never see that. I also introduced this to my MA1 student. Why I introduced this example? Because you can see that this function, right, is continuous everywhere except 0. So you want to ask whether if I define a limit point here at 0, can I make the whole curve continuous or not? Okay, because now we just consider the positive path. If negative path also looks similar like this, very far and then oscillate very close. So can I just add one point here and then make it continuous? And not why? Sorry? You have two subsequences that converge to different limits. Okay, but in general topology, we can solve this limit point. What's the limit point of this graph? The whole interval from -1 to 1. But to define a function, you cannot do that, right? I cannot send a 0 point to the whole interval. I cannot do that because 1 point only can go to 1 point. So actually the limit of this graph is like the whole interval. But I cannot define using function. I cannot send 1, 0 to the whole interval. Does it make sense? The straight line. I cannot send 1 point to like infinitely many points. No. Unless your codomain become a interval. Unless you work in different setting, maybe you can make it continuous somehow. I don't know what kind of continuous is that. But okay, anyway, so let's do this. How is it? Also, since you guys already know, so how to prove it? How to prove? So you guys should know, is it? How to prove? Contradict, so how to contradict? Or maybe you come and teach. Come on! Wait, you learned before, eh? Come teach me how to do it. I'm serious. I'm serious. So how to prove? How to prove it is not path connected? Sure. We define let's say we suppose it is path connected first. And let me see. Right. So sure, we haven't finished defining it. So we haven't finished defining. So it's not just S, it's X bar actually. Okay, it's not just X, it's X bar. So you take the closure. Okay, so this, yeah, without bar, no sin first. With bar, sinful. Okay, yeah, with bar, very sinful, this thing. Okay, so how? How? So add this line in. Okay, let's add it in. So let's call this S bar. So meaning what? I can, so in this oscillation here, for any 2 points, I can find a path, right? Like for any 2 points here, I just follow the graph. It's my path. So the problem is what? The problem is the point on this closure and any point on that oscillating. Okay, so suppose we have a path from any point here. Should we pick a special one? Do we want to pick a special one? 0, anything, it's okay. So pick this one, maybe any point from here. Let's say we have a path. I don't know how, but there's a path. Okay, that goes there. Continuously, very important. Not continuous, I don't know, maybe good thing can happen and can happen. So must be continuous. Okay. So what else? So suppose there's a path. I think we'll spend like 10 minutes to talk about this. So suppose there's a path from for convenience, can I straight away take it from 0 to 1? Going from 0 to 1 to x bar, connecting 0, 0, and a point in S. Okay. Is the point important? Not very important. Okay, let's do it like this first. Okay, about just name it name it S maybe. And then this one 0. 0. 0 happen. So this one without loss of generality. Okay, I will treat it more carefully in my notes, but I want to fix my domain so that I have a right domain. Okay. So what kind of contradiction I can get here? To what? Yes, contradiction to the continuous path. So you see, let's say I have a path like this, right? Let's say, and then connect here. Why there's a contradiction here? So you can, well, what's the continuity argument here? For every sequence that converge to 0, Fsn have to converge to F0. Okay. But you can take sequence of Sn that converges to 0 from the top, and also you can take sequence converges to 0 from the bottom. What do I mean by from the top and from the bottom? So you can pick, so let's say here. Okay, so let me take out this subsequence here. So here correspond to some point at the bottom here. And then the bottom part correspond to some point, some purple point here, right? You can see that the purple point and the orange point all converge to 0, right? But f of the purple point is always -1. F of the orange point is always 1. So your FSN got two subsequence that converge to different limit. So your FSN cannot converge to F0. It makes sense? So it diverges. Okay, so there's a contradiction with the continuity of the task. So this argument is really similar to what we have in MA1. Okay, but more advanced thing in our course is we can take limit point of the curve where we get the interval from -1 to 1. Okay, does it make sense? Yeah, so there's no path, no continuous path. Okay, I think for today we will just stop at this point. And then next time, I think we will go straight into compactness. Yeah, sorry. Like that? Yeah, I think we prove it. We prove it. I think we did it once. We did it once when we introduced connectedness. The first day we introduced in connectedness, I proved that first. Yeah. If not, I just send you the lecture notes. And then we mention it again when we do the second lecture. We didn't prove, but we mentioned it again. Yeah, yeah, yeah. That's not quite good. Huh? Say again. So let me write down what you say. Huh? So open. So from where to where? What set? So okay, in what set? Your S. Like that. So you mean this is the inverse of something? Depend on where you want to put it in. If you put it in the whole space, then it is not. If you look at as a subspace, then open. The path one. Oh, you mean this path? This path. So this is open. Wait a minute, let me see. Oh, is let me think. It's open. Yeah, open. Because you regard this as a subspace topology, right? Regard this as a subspace topology, and then you just intercept -1 to 1 open neighborhood with this one. Hmm. You regard this as a yeah, subspace topology of R. Okay. Question or not? You know what I'm talking about? I'm like saying like this. If you read, yeah, I think we regard it as a subspace. Okay. If you put R here, that's a different story. If you put R here, then it's a different story. Because you look at the whole space, not the subspace. So that's why we have a topic on topological subspace. Metric also have metric subspace. I didn't introduce, but there's a similar notion. Okay or not? Any question on path connected and connected? The other is not too important. There's a small portion of your book talking about what is locally connected, what is locally path connected. I think not so important here, but in future, maybe if you want to do pure maths research, maybe you need to go to that detail. Okay, you want to talk about locally connectedness. Okay, locally is a connect. Okay. So maybe I read it out. So a space is locally connected at X if for every neighborhood U of X, there is a connected neighborhood V of X contained in U. So if you want to say that X is locally connected at X, so you just need to prove that for every neighborhood around X, open neighborhood, there is a connected open neighborhood again contained inside U. Okay. Yeah. For now, I think not very important unless we need to build something. Usually, they want to use this property to build a whole space, something like that, or to deduce connectedness in general. But for now, I think we don't need to go to that detail. Or maybe it's a very good assignment question. But our assignment is still long. Maybe I will skip this kind of thing. There's more important thing to do. Yeah. If you're interested, you can look at it, but not too important. Yeah. Unless we're going to use it, then we will do it again. Otherwise, we won't do it. Okay. Your question? If not, let's take a break until 1:22, and then we will resume discussion. Hello. I think. Hey, do you guys watch anime or not? Yes, sir. I'm gonna show you Demon Slayer. Huh? Good. Can someone close off the light? Yeah. Is that one? This one. No, the clock. Yeah. Yeah, I show you this scene. Shrinking. Let me try. Oh, okay. I know what's going. Okay.